Okay, so I've mentioned the assumptions underneath the linear model before, but what we haven't done yet is see how we're going to check whether the assumptions are met, or to what extent are they violated. Just briefly then, let's go over the assumptions. We've got our independent variables, the ones on the x-axis, are measured without error, fixed x. That one's almost always violated in in practice, but we ignore. It's very common to ignore that violation. Errors are independent. That is, the error from one observation doesn't tell you anything about what the error or the deviation is in the next observation. Errors are normally distributed, have a constant variance, and finally that the relationship between the x variable and the average y is linear. So let's take a look at each of these in turn. The way we check most of them is by graphically examining plots of the residuals. The residuals, recall, are the deviations between the average value of y predicted by the model and a particular observation, the little E sub i's. One easy way to do this is to look at a histogram of the residuals. So this is sort of a way of visually testing whether our residuals are in fact normally distributed. And you can see there's more residuals close to zero than there are far away from zero, and it's more or less symmetrical. It's not very easy to judge whether that's a good fit to a normal distribution or not. But it's one thing that you can do very easily to check your models. This is sort of a better plot. Makes it much easier to check whether things are where they ought to be. It's called a quantile-quantile plot. On the x-axis are the theoretical quantiles, so that's where would this residual be in terms of a standard normal distribution if the variance was known and it actually comes from a normal distribution. On the y-axis are the sample quantiles for each of the same data points. And so what should happen if the model is actually, if the data in fact do have residuals that follow a normal distribution, then everything is going to fall along that straight line. And what you can see here is that there's some deviations in the tails. In particular, there's some quite extreme points down here and this one up here. That in and of itself is not necessarily a bad deviation. By and large, over the bulk of the data, it is fitting pretty well. R actually allows us to get these plots, or a couple of these plots, plus some other ones, very easily by just using plot and the result of the fitting function. So let's go through these plots one at a time. The normal quantile-quantile plot is up here in the upper right. Over to the left here is a plot of the residuals versus the fitted. So now the error is plotted on the y-axis, that's the residual, and what's plotted on the x-axis is the predicted mean value for each observation. That's where the line is for the predicted value. If our assumptions are correct, the points should be scattered evenly above and below this line, and it shouldn't matter whether you're close, whether you're down here or up here. There you should just have a nice even sort of scatter. And to help you with that, there's a sort of smooth line that's been fitted through here, so this should be flat, this line, and close to zero. And again, it's not too bad. There are 3 points down here which are labeled with the observation numbers, and that means that R has concluded by a variety of different metrics that those points are extreme relative to the observations. Let's have a look at what we've got going on down here. This is a sort of a trend. It's basically the same as this plot up here. It's called a scale location plot. The difference is that the x-axis is the same, but the y-axis has been rescaled in 2 ways. First, they've taken the absolute value of the residuals and then also scaled them by the estimated error in our model, and then taken the square root of that. All of that together means that if our average residuals should be falling around a value of 1, with standard deviation of 1. And it shouldn't matter whether you're, it should be flat. There shouldn't be any trend in these things. So it doesn't actually look too good for us here. So this red line, again, a smooth fit, should be flat, and it's not. We've got some large outliers dealing with up there. This plot here is particularly sensitive at detecting the departure from the assumption that our variance is constant. That's really what we're also checking for up here. This top plot is also useful for checking the assumption that our relationship is linear. If there's a sort of systematic deviation in our residuals as the fitted value changes, then that might indicate a nonlinear relationship between the x values and the average y. Okay, so that just leaves us this last plot over here. Again, we've got our standardized residuals on the y-axis, but now not the absolute values, so there's some of them are negative and some of them are positive. And then what's plotted on the x-axis now is something called leverage. Leverage is a measure of how much an individual observation influences the fit of your model. So if you have a very low leverage, which most of our points do, if you take that point out, the fitted model is not going to change very much. In contrast, if you have points that have very high leverage, like these ones over here, and particularly this one up here, it means that if you remove that point, the model fit is going to change by a fairly large amount. And what we would worry about is points like this one, 141 up here. It has high leverage, and it has a fairly large residual, which means that it's poorly fitted by the model, and it's having a large impact on the result. And that's a double whammy. That's what these dashed lines here are sort of trying to indicate something else called Cook's distance, which is another measure of that impact. And so you can, if you've got points that are sort of really far out in these corners with large Cook's distance, then those are ones you might want to consider removing. So just out of curiosity then, so that's that point 141 up there. Let's get rid of it, and also those other three extreme points down there. And what I've done here is just replot the fitted line. So it's changed a little bit. In particular, it's no longer, it's a little flatter, the slope, right? So before it was a bit higher because it's trying to get close to that point up there. And now it's sort of tilted a little bit. So the dark line in the is a little bit lower, or tilted a little bit flatter than the dashed line. And if we look at our quantile plot, we see it's actually much improved. It's really come out very different. And our residuals versus the independent, this is also a good way of checking to see if our relationship between the independent variable and the model and the average value of the y, if this thing's not flat, then that's an indicator that the relationship's not linear.